So thank you very much. I am Horibe from G-QuAT AIST. Thank you very much for giving me this great opportunity. Yes, Tanaka-san was talking about G-QuAT, and from here, I'd like to talk about our mission and what passion or philosophy we are adhering to. So first of all, this G-QuAT type of hub is being developed in different countries, and this is because each country is also steering toward industrialization of the quantum computing. Well, maybe some people may have some opinions on this, but to be more accurate, well, the basic research is going to be accelerated, and that's a given. And outcomes are now trying to be expanded or deployed to their commercialization or industrialization. Each country is now building or developing a hub in different locations, and each hub might be unique in different characteristics, and there's no identical hubs everywhere. But maybe one thing, especially for the quantum computing innovation to be enabled, what is needed? Well, the talents and also exchange of the talents and networking of the talents. We have to have the good collaboration or alliance. So that is necessary. So that's why we have to connect the different hubs of different country. And this is what we are trying to endeavor as our mission of G-QuAT. So as I showed on this slide, and yes, LOI or MOU have been already concluded to a certain extent, and also other countries are already in the discussion to conclude MOU or LOI. So we are now trying to develop the network which is connecting different hubs in different countries. And yes, not just researchers like you, but maybe the startup or the business players in different region or different country. We should really expedite the exchange or networking of those talents, and that is what we need to do. What is required for innovation to happen? Well, this is currently the Cabinet Office, the experts panel of quantum technology innovation under the Cabinet Office is currently discussing on this. So workforce and resources, especially for the testbed, or accessibility or access opportunity to the testbed, and also finance. So those are the three elements which have to be connected. Well, yes, when we discuss all of these, and yes, I'm sure that you have different opinions on this, like this person. Well, even this person is also saying the same thing for the innovation formula. And this is sort of the timeless formula for any innovation to happen. Well, industrialization is also expanding, and METI has the innovation committee, and they already have an interim report. Innovation model is now changing. It has changed over time. So in the past, maybe the basic research to applied research and then commercialized. But right now, we have to have all of them in parallel, and even in the business area, the winner in business area will have a certain influence onto the science arena. So that's currently what we are seeing. So basic research is basic research, and application is application, and social implementation is another. If this is siloed, we will lose. So that's why G-QuAT is trying to connect from basic research, application, and social implementation. We are supporting end-to-end pathway. So one of the elements is resource, as I mentioned. Well, yes, we are supported by METI and buildings, of course, but the NVIDIA H100 GPU, over 2,000 GPU HPC is already developed. This HPC, well, for the QC social implementation, this is purely for the QC implementation. In other words, so this is a first GPC just supporting the quantum computing deployment. So I hope that they use this. And also the quantum computing operation. So one in the yellow, the sentence in the yellow, when it used to be that, yes, quantum computing usually is based upon the national project, and that usually is given. But in reality, for people who are not relevant to the national project, we do have the accessibility to those people, but people may wonder if they are eligible to use the quantum computing, which is developed under the national project. Well, our resource is supported by METI, and we have this great facility. So whichever project or whichever constraints, we don't have those. So yes, it can be used for the national project, or maybe it can be used for the specific company's computing resource. So we allowed both. So this is really important to accelerate the use cases. And of course, it can be used for the national project or national policy. So yes, NATO challenge, which was introduced in the previous presentation. Yes, we are offering the computation resource to those projects as well. Well, this is the new buildings. And the first floor, we have the ABCIQ, GPU, and then we have the superconductive QC in the next building. And then we have the neutron and also optical computing in the third building. And we have the high-speed network connecting so that we can enable hybrid environment. This is a cutting-edge tool, and also it's a little bit embarrassing, but in Tsukuba, well, Japanese representative research city, that's what Tsukuba is. But they did not have any quantum computing before we established this facility. So now it is established, and also a different industrial exit. So the research centers, those will be using this type of resource. That means the leading research facilities in the different industry, they are able to start the research for their arena using this quantum computing resource. Of course, research institute is really important, but when it has to be industrialized, it has to create a collaboration. So that's why we have the incubation area on the third floor. We have different stakeholders coming in so that we can accelerate the alliance. Sometimes it can be user, supplier, or vendor. And yes, we have been talking to the different venture capital companies. So yes, that's what we have already. Well, the mission or the activities of G-QuAT, we have the 8 strategic activities, and also we have the 6 strategic outcomes. At the end of the day, what we are trying to enable is establishing global ecosystem. And let me share some of those. Global collaboration. Well, yes, we already concluded MOU LOI with different financial institutions, different research institutions, and also different companies. And yes, we have some others which are also under discussion, not described here on this slide. And as I mentioned, the global hub network to be established. And yes, that will be also included. And yes, within 2 weeks or maybe in 1 month, we can actually make announcement, at least one of these in every 2 weeks or every 4 weeks. And when it comes to the incubation, well, sometimes incubator or maybe VCs coming in. So it's not just simply the residents of these facilities, but trying to set up the mechanism so that the business can be created from here. And also, competitive environment is also required. Yes, incubation and collaboration is one, and this is really important. Why? Because trying to really establish the market for the business, and that requires collaboration. And then after developing the market, then each company should not just be friends, because otherwise it will not develop. So on the business foundation or infrastructure, they should be competitive. They should compete. And maybe one method or methodology is that the ABCIQ, which is our GPU, it should not be just for the classical computation resource, but yes, it can be used as gateway to connect different quantum computing. So users are coming to access to the ABC IQ, they will be able to access to the different quantum computing. And this requires middleware development. So middleware tier, of course, we have to have the open-close strategy. And then, as I mentioned, standardization is really important for that. So when we have this kind of environment, what's going to happen? Well, user coming to access to ABCIQ, to access to different methodologies QC. From the user perspective, there are different computers or different methodologies with different unique characteristics. And that way, users are able to do whatever users want it to do. From the vendor's perspective, well, yes, coming to our site and they bring their QC and then connecting to ABCIQ. Just by connecting to ABCIQ, they can actually access to hundreds or thousands of the users who are accessing to ABCIQ. So as soon as possible, vendors can start their businesses. This is win-win situation. Users are able to access to different quantum computing. And yes, maybe sometimes it can be a neutron, sometimes it can be the superconductive methodology. So it is kind of chosen by users, which is creating the competition. So that's how we are trying to expedite the competition. So I have been talking about a little bit about conceptual side, but now, to really achieve or attain the industrial level quantum computer system, what are the hurdles? What are the challenges? Well, yes, when it comes to the larger scale for different methodologies, yes, for each type or each methodology, they have the challenges, especially in the engineering part. Well, the superconductive is something which I'd like to focus in my presentation, talking about the challenges and also solutions. And then lastly, I also would like to talk about the neutral or ion trap and also the optics or photonics quantum computing. Well, yes, even right now, the scale of quantum computing, if we talk about the size, you usually talk about the physical bit, but because of the FTQC, I think we should change or shift to the logical qubits. Depending on the methods, the logical qubits, the number of the physical qubits required is different. And this also depends on the algorithm. But yes, the superconductive roadmap and ion trap roadmap, if we see the mapping of the physical qubits, that's on the left-hand side. And yes, we are going to also roadmap for logical qubit, ion trap, and superconductive. It's quite similar in logical qubit, although they are different in physical qubit. So how much the size is required for logical qubits will be clarified. Well, in 2030, we want to have 1,000 logical qubit. And if we are going to enable that, then what should we do with the superconductive? Well, yes, the superconductive QC, quantum computing right now, the dozens of millions Kelvin, we have a lot of cables. And if we're going to make it larger, then cable is going to be more. And by having more cables, that actually means that the heat is going to be generated. And we have to make the larger refrigerator, and also we have to have a larger cables. And at the commercial level, the affordable icing or maybe the refrigerator is Blue Force Kiden, and this is for 1,000 units. But yes, this is a 9 for Colosseum. And if we're going to do 1 million, then it will require 9,000. And then this is also coming from the Google, and it's a huge. As you see, it's like a gymnasium if you compare against the size of the human being. And also the price and also power consumption. Well, for instance, this KIDE and also FPGA-based QCS is utilized for 1 million qubit for 300 days, then it will be 1.3 billion kilowatt hour per year is required. And this is one thermal power plant, equivalent to one thermal power plant, and it requires 8 trillion yen. And then that is the same level of the budget of the Tokyo metropolitan government from the last year. So, well, it's a huge task, but we don't have to give up. So size and also weight. Oh, yes. Maybe the cryo CMOS can be utilized. And then, yes, 2400 is required. And then, yes, at the end of the day, yes, it will be heavier. But Boeing 787, 10 of them is equivalent. And also the area required is the entire Tokyo Station building. Well, what I'm trying to get at is we will not give up, but in order to industrialize, we have to continue researching on the qubit. But in order to do the integration, the materials or equipment, we have to also make them advanced. So let's say the pulsium can be smaller or maybe more efficient. That could be one solution. And also new refrigerator can be developed. That's another solution. So it will be economically reasonable, and that's the one major requirement for industrialization. I'm not talking about the negative factors so that we have to give up, but rather we have to be aware of these facts, and then we want to engage and involve different players in the industry. So what kind of methodology are we looking at? Yes. This is not the final result. Maybe the interface can be optics or cryoelectronics can be utilized so that maybe the controller can reduce the power consumption. But if we are going to use cryoelectronics for everything, it will also have a certain impact onto the refrigerator. So we have to design the entire system, but how each part can also improve for its performance. And yes, other component manufacturers also have to be involved, but we need to design at the system level. And also, in the future, yes, we will be providing a lot more detailed information in the future, but photonics or neutral atoms and ion trap, they all have different challenges. And also the quantum computing, I'm talking about quantum computing only, but quantum computing is used in hybrid with HPC. So that is sort of the de facto use case. So how we are going to integrate with the data center is another challenge. One more time. Engineering is not the only solution, but qubit itself has to improve its quality and performance. So once again, we need to continue the basic research. And this and also engineering have to be connected deeply, and that's the basic requirement for industrialization. So what should we do with the component or parts development? Well, G-QuAT, yes, we set up the quantum computing, but of course, the components also need to have the test bed for the evaluation for the new parts. Well, AIST, we have the measurement of the measurement facilities to really evaluate. And then at the end of the day, we would like to have the certification system for the components or parts. Well, test bed, from the manufacturing technology to the evaluation of the parts or maybe evaluation of the system. And currently we are setting that up. And yes, I cannot show the picture yet, but the Blue Force KIDE will be implemented, and also FPGA-based QCS, 1,000 qubits will be also set up. And this is for superconductive and also silicon method, but ion trap and also photonics and also neutral, different components for the different methodology can be also evaluated at our site. And also regarding the quality control, yes, at the device level and material level and module level, yes, of course, the system level, we need to collaborate with vendors. So yes, this type of framework is available. And then this is the last slide. Yes, I did not really talk about the use case today, but the computer resource will be provided so that different researchers or maybe the different industries are able to use these resources in our site. So by making use cases, if you say the challenges which you are facing can be fed back to us so that it can be fed into the next generation development. And for that purpose, we need to really have a good relationship with the suppliers as our mission. Yes, I have been talking about all of these, but use cases or creating or developing the quantum computers or even developing the parts, main player or protagonist is you, companies. We are supporters. Please use us trying to really develop the industry of QC. We have the booth, so please also stop by. Thank you very much. Thank you.